Oh my god, I just recorded the best video. The best video. I'm serious. It was. It was the best video, and it got deleted. It got deleted. I don't even know how. I don't know how because I went through the process of like recording it to try and see and try and debug and try and see if it could be prevented in the future. But now it is just like, huh? Can you guys see notifications? I wonder. I don't know. Maybe I should disable that. But I'm talking about like, oh my god, my alarm is going off. Okay, whatever. My ADHD meds have worn off. It's getting close to bed, but even so, I had an amazing video. I mean, it was distracted as fuck and wandering, but then I got into a flow, and it was so good. It was so good, and it captured a moment of like thinking through and realizing something very, very cool. I suppose I'll talk about it. I guess I'll just go through it and like, but you won't get that moment. You won't get that moment that I had of like realizing a thing. I don't know. Maybe I'm overselling it. Am I overselling it? Well, you'll find out. Okay, Maxwell's equations. Some very cool connections that I had made. Main thing is the connection. Okay, it is still very cool. I'll still get to talk about it. It's a-okay. Everything's fine. Is the connection directly between two of Maxwell's equations and the wave equations. I've seen before some derivations trying to get the wave equations from Maxwell's equations in Maxwell's equations in its dynamic form, right? In its static form, it's just these time derivatives are zero, right? And that makes it so that there's only one doohickey, only one term in this equation, which makes it slightly more symmetrical looking. But and if there were magnetic monopoles discovered, then it would be even more symmetrical looking, and it would be lovely and beautiful. But we're not there. It's okay. It's fine. Everything's fine. So one cool thing is that the two wave equations can come directly from the these two of Maxwell's equations. Here are Maxwell's equations. They are lovely. They are cool. These are ones that are fundamentally static. Fundamentally static equations. Gauss's law. The Gauss's law for the electric field. Gauss's law for the magnetic field. This is the two curl equations happen to be dynamic. Well, actually both of these are dynamic. Yes, that's right. Okay, that's an interesting thing. I hadn't really noted, right? Both of these terms are fundamentally dynamic because this is the differential version of the current, which is the change in charge, the change in charge over time, right? So both of these are time derivatives essentially. But in any case, let's talk about free space. J equals 0, rho equals 0. No current, no charge. And how you can like just look at these two, right? So notice that this is the this fourth equation, right? Where we have because this is this fourth equation here, right? Where I'm just setting the J term equal to 0, saying there's no current at any point in space. But what we can do is like one thing to note is that C is equal to 1 over epsilon naught mu naught. And that comes that comes out in the derivation, right? Somewhere in this derivation, right, this epsilon naught mu naught here ends up in the spot that would indicate there being a proportionality constant that relates the second order spatial derivative to the first order time derivative, which is kind of fundamentally what a wave equation is all about, right? And that somewhere in that wave equation, you'll get a time. What am I saying? You'll get a proportionality constant that'll correspond to the speed of that wave's propagation in meters per second. And that from that derivation that was labeled as C, but here at this point, right, we can just come directly from Maxwell's equations of epsilon naught mu naught. But for the sake of the argument I'm trying to make, let's just take as a given, right, that C is 1 over epsilon naught mu naught, right? And so that means that we can rewrite those two dynamic Maxwell's equations like this. All I've done is replaced C with 1 over mu naught epsilon naught. And here's the big thing. Okay, so at first I was thinking, I had the thought, like, hey, curl, and curvature seem pretty dang similar qualitatively, right? So I was wondering, are they mathematically related? The answer is no, but like, why not? But at least I'm pretty sure the answer is no, based on the reasoning that I had done. But like, the idea was that like curl fundamentally, right, is sort of relating two different, or fundamentally, it's fundamentally at least two-dimensional, right? Has to be sort of relating the behavior in one direction with the behavior in other directions, right? Any term in the curl equation is talking about the spatial derivative in one direction of the field in the other direction, right? So it's in two dimensions. It'd be proportional to this. I don't remember if it's flipped or not. Maybe the negative sign is the other way, but like, yeah, it's relating spatial dimensions to each other. Right. And I was thinking about like, if it wouldn't make sense, right? It wouldn't make sense that that they are related. Because these are the three ways of like talking about a first order spatial derivative in the context of vector calculus, right? And to my knowledge, I think there's only one way of talking about, or of defining a second order derivative, right? But then that's unclear. That's a second order derivative of a scalar quantity. Is there? I wonder. Are there second order analogous operations to the divergence and curl? Right? Of a field. Right? What do you do to a field in order to express its like, in order to express its second derivative quantities, right? Maybe is this a thing you can do? Can you do gradient squared? Well, Well, oh, I think I remember you can do gradient squared E, right? That'll just result in a vector of taking the Laplacian of each component. That's a vague memory. It might be completely wrong, but I think that's right. Anyway, got distracted. Oh, but then, but, what's the second order analogous operation for the curl operation? What would it be? The Jacobian? I don't know. The Jacobian? I don't know. What is a Jacobian? Is it I know the Jacobian is like a higher order generalization of spatial derivatives for sure, but not necessarily spatial. I mean, it's a mathematical construct, so it doesn't necessarily have to be spatial, but it could just be any quantity. And I know that it can handle multiple. I know it can handle high dimensional output spaces. Can it handle high dimensional input spaces? I believe yes. Yes, it can, right? Because I know that it's a matrix. Okay, interesting. So maybe the higher order analogs it's probably the Jacobian, right? And I would imagine that's maybe it's a square matrix. Maybe it's a square matrix where the diagonals correspond to the Laplacian. Interesting. And where the cross terms maybe correspond in some way. To like analogous, or things that are analogous to the curl operation. I don't know how that works, so let's explore that for a second. Okay. So let's say it's a 3x3 spatial matrix to represent. Let's do a two-dimensional space. That sounds like less of a headache. X and Y. That's all we need. And we're talking about the Jacobian for that. And then maybe there's some D squared, right? A second order Jacobian. Is that a thing? Surely there's higher order analogous operations to the Jacobian, right? I don't know. What is the Jacobian mapping, right? The Jacobian is a matrix, so it's probably mapping some vectors from some vector space to another, right? Right? How's a Jacobian defined? Okay. Let's take a look. Okay. All right, so it's df1. All right, so is it defined as it relates to a vector field? Yes, right? It's Rn to Rm. Right, okay. Yeah. So it's super versatile. It can be any dimension input space to any dimension output space. And they don't have to be the same. So this doesn't have to be a square matrix. It's just that I would guess that this will be the most the most applicable for us, and in terms of how it relates to electromagnetics and being in a three-dimensional world. So df dx1, yada yada, and then the top stuff is all going to be df1. So I'll say like dex, right, and all going to be dex, and then going down is going to be with respect to x, y, z. So the Jacobian for a two-dimensional space, right, is basically going to say that is basically going to say it'll be d e x d e dx ey, and then right. And right, one could write that also as so surely the thing is those. I referred to something in my head that made sense to me. It was a connection. I'll explain in a sec. Maybe I will. Maybe I won't. You'll never know. Okay, so the thing is, right, this is a dot product of a, clearly this is a dot product of an operator. Is it? No, it's the opposite. It's whatever thing you do. Oh, it's the multiplication of a row matrix and a column matrix, but in the wrong way, isn't it? Right? Because if you multiply a row matrix, let's say of length 2 with a column matrix, a row matrix of length 2 with a column matrix, the way matrix multiplication works, so you're just going to take the dot product of those, and that's just going to generate some other column matrix, right? But if you do it in the other way, you put your column matrix first, that's going to generate a whole 2x2 matrix, right? Where this, the multiplication of that gets that, right, gets that gets this one, and that gets that one. And so that could be how you generate this matrix here, right? So thinking about that, maybe I could kind of represent this del operator in 2 dimensions as a column matrix being multiplied in this order with a row vector here. Huh. Neato. Right? Wouldn't that make sense? Would that make sense? Yes, I think so. So, but then if you write this, can you write it like that? Is that a way to think about it? Can you write that? Because it's kind of like the gradient vector. You could read this off as like, this is this column, this column vector of the matrix, it represents the dot product, right? No. This column of the matrix represents the gradient of EX, right? This gradient of that scalar field, okay? And this is the gradient of that scalar field. Where am I going with this? God knows. God only knows. Right, d squared. Isn't that what we're trying to do? Maybe. Yeah. My thought that I had that I said maybe I will tell you about. I think I still have it. The idea is that surely d squared is a thing, right? And surely it corresponds to this. And surely the diagonal sum of it corresponds to the Laplacian. Ha 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 ha. I bet that's how it works. Surely that is how it works. Right? This is that. Right? Because these diagonal terms are going to be the ones where everything, where the direction that we're still doing just 2 dimensions. Keep it simple. Keep it simple. Right? We're not interested in your complicated BS. Okay. In this direction, we change the subscript. In that direction, we change the partial derivative. Change the subscript. Change the partial derivative. Right? And if we think of the diagonal, I'm sure there's a piece of notation that that's the diagonal. I remember it. Ah ha ha ha. It's the trace. That's what it's called. The trace of this matrix, right? Where you just take the doohickeys on the diagonal and add them up. Right? So that's just going to be this squared plus that squared. Hey. That, my friend, is the divergence of E. No. The Laplacian of E. That's it, isn't it? And, I don't know, the cross terms could somehow represent the, I don't know, what would represent whatever sort of curl nonsense there is. I seem to remember. Well, hold on. Now, this doesn't make sense to me, right? This, whatever, maybe this isn't how it works. Maybe this is missing some information, right? Because think about it. Think about the other cross terms. These aren't the only cross terms, right? Because shouldn't there also be terms with del x, del y, right? If we look at the scalar field E sub y, right? That's a scalar field at every point in space. What about saddle points, or things describing that? It's a horrible. What about saddle points? Things describing that behavior, right? It's got to have some del x, del y, right? We need something to describe those things, right? We need something with what would it be? 8 terms, with all the combinations of the permutations between EX, EY, and the right, and the thing of dx squared, dy squared, dx, dy, dy dx. Right. So something with 8. Right. Right. I don't know. Well, let's look back on Wikipedia. What does it look like? Jacobian determinant. Can it talk about higher order things? Yeah, yada, 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 yada. I don't, okay. Dynamical systems, blah, blah, blah. What am I talking about? What are you talking about? Can I just Google higher order version or higher order analogous operation to the Jacobian? I'm gonna read the, or no, okay. Derivatives of, there you go. That's much better. That's much better. Derivatives of the Jacobian matrix. Oh, okay. The Jacobian matrix is called J. Neato. I didn't know that. Okay. DJ dx. Oh. Okay, yeah, okay, gotcha. This is an n by n by n dimensional tensor. Right. We would need tensors to describe this because we need a mathematical structure that, unlike a matrix, which is two-dimensional, we need the structure where the numbers are organized into a three-dimensional space, right? A three-dimensional rectangular prism of numbers. That's how we need to describe it. Where this axis is the component of the vector that is gone through. This is the thing that you are. This is like maybe the thing that you are deriving with respect to first, and then whatever into or out of the page, right, is the thing that you are deriving with respect to second. Huh. Neato. Huh. Well, you learn something new every day. Every single day. Except for when you don't. And those are not good days. Okay. And then so I guess the trace of that of that tensor. I don't know. You need to find the trace of the tensor. I don't know. I wonder what pretty little patterns would come from looking at a tensor like that. Who knows? I will glance at it. I'm getting tired. I will not dwell on it. Nope, I'm already bored. Okay, never mind. And it's 10:12 p.m. That is too late. It's too late, and I need to be done. This was fun. This was cool. I didn't even get to the explanation. Fine. I'll do the thing that I set out to do at the start, and I'll explain this, especially in the context of antinodes in an electromagnetic wave. Okay, because it's a very, very cool thing to read it off like this, and I want to share that. So I'm talking about this antinode. This antinode is the place where all of these quantities are maximized in terms of their magnitude, not necessarily dealing with the sign at a particular of a particular field at a particular point. Just don't even worry about the sign. I'm talking about the magnitude of these vector quantities. So, but if we look at this antinode, right, this, for sure, let's take a look at the electric field in this wave. I might have drawn this wrong. In terms of, like, should I have drawn it? Well, I didn't even tell you if it's going to the right or to the left, so there you go. Oh, and I just remembered, the way I've drawn it, it would be going to the left, wouldn't it? Because you got to do E cross M in order to find the direction. Anyway, that's not what we're talking about. What we're talking about is, like, look at this point, look at it, and look at the pink, lovely pink magnetic field here, right? That is a point, right? That is at a maximum in terms of the time derivative, right? Because, like, time derivative, right, we're only varying time, we're not varying our position in space, so we're just looking at this point in space, and we're looking at how when it's like big like that, it's like when it's going all the way up and kind of coming to almost a stop and then going back down, right? But then when it's going down, that's when it's going whoosh and shooting through, right? That's where its maximum time derivative is going to be. Is when it's wherever it's at an antinode at a given point in space and time. And so now we can also see that this point will correspond to the a spatial derivative in the electric field. And let's take a look at this. The electric field here, right? You can just see. Look at the slope. Boom, maximum. That's all, right? Here slope. Here curls 0. Here curls maximum. Just visually, you can see that in terms of the slope of that line, right? And so that is relating this temporal, this relationship between the first order temporal derivative of b and this first order spatial derivative of e, right, and vice versa. So that tells us that right, that tells us, this tells us that they got to have this like sort of orthogonal quality, right? It depends on, they depend on each other's orthogonality relative to themselves, right? And well, hold on, or their dependence on each other is spatially orthogonal. That's what I should say, right? That's a better way to say it. And the I don't know. Oh. So yeah, that's very cool. The other connection, right, is like, okay, so in a wave equation, the main thing of a wave equation, right, is dealing with a first order time derivative and it should relate to a second order spatial derivative. And I know that and at first that was like kind of confusing because I was like, oh, well, this is all first order spatial stuff, right? I've kind of shown to myself that, like, no, this isn't directly related to the Laplacian, right? Curl and curvature are two different things, because curvature is how curvy is this thing in a dimension, right? Right. That's still talking about like sure, it's relating to quantities to each other, right? Two spatial directions to each other, right? But like only if the thing we're taking the second derivative of is a spatial direction, right? If it's just some vector, or if it's just some scalar field, we're only dealing with one of them, right? Because like here, the notion of curvature, right? We'd be talking about curvature of this graph, right? But that doesn't, the only spatial direction of that involves is x, right? Because this other direction is totally imagined, this representation of the numbers. So whatever second derivative you're taking with respect to x, for example, is only going to be dealing with just, whatever you choose here, right? So you could totally just do that, right? Anywho. Was there anything else that I missed? I don't know. There were some cool connections I made up here, but I don't feel like talking about them because I've been talking a while. And I'm fucking tired. Okay, good night.